before I actually joined the Forta Foundation, I worked at Microsoft on their Microsoft Defender suite. And I was there for many, many years. And when I initially started there, it was the Windows Defender group, which was essentially Microsoft's antivirus solution. And the group primarily consisted of security researchers that essentially analyzed malware and authored essentially anti-malware signatures that shipped with the product. And that worked very well. But what became clear over time, and especially as more data became available, that protection value could come from machine learning and data science. And today, that group is about 50-50. It's 50% security researchers and 50% data scientists that are building protection machine learning models. And I very much expect that in Web3 security, kind of the same progression needs to happen. And the big advantage of Web3 is that the data is really public. Compare that to an entity like Microsoft, where a lot of the data is proprietary, cannot be shared. Here it is public, and that really opens it up to the community. And what we're trying to do now is really to attract these data scientists to build on top of Forta. You may have seen that we just published a Kaggle competition. Kaggle is a data science platform that is well known in the data science community. So we published a data set and invited that community to really innovate and develop algorithms and models that identify threats. Sorry, my dog is already here shaking. Now, if I look at Forta and the bots that are deployed on the Forta network today, primarily they're heuristic bots. So these are generally coarse conditional statements that were created based on expert knowledge to identify attack behavior. I personally have authored many bots like that, where maybe I have one example of an attack, and now based on my expert knowledge, I kind of carve out some heuristics that I feel like will identify similar attacks going forward. So the example that I mentioned here is a flash loan contract is included in the transaction, and the token movement value is above a threshold. That's an example of a bot that exists today. And I think that this approach works very well, especially if you don't have a lot of labeled data. Taps, of course, into the expert knowledge of the bot developer. The alert is very explainable, right? You know exactly kind of the condition that it triggers on, and that allows you to expose an alert that is very descriptive. But kind of the downside of this approach, that it is biased. Like, I am using my expert knowledge and encode it into heuristic. That is biased. I make a lot of assumption, and so maybe I will not kind of detect the attack in a generic way. And then the other downside is, as an expert and a heuristic, there's only so many conditions that you're able to encode. So the alert itself is quite coarse, leading to low recall and precision. And by recall, it's kind of a data science term that means the percentage of attacks identified. So we have 100 attacks, 50 are identified, so the recall is 50%. And precision is the percentage of false positives in the alerts raised. So let's assume a bot raises 100 alerts, and 10 are true positives, so they are indicative of an alert. That means a 10% precision. Overall, we of course want to have high recall and high precision. We want to detect most of the attacks, while at the same time not raising a lot of false alerts that would result in alert fatigue of the consuming team or the consuming process of these alerts. So that's heuristics. And so what machine learning does, it utilizes an algorithm that is trained on past data to make predictions on unseen future data. And it is it can be used if you have labeled data Now, in our space, we don't necessarily have a ton of labeled data. We can look at Etherscan tags, for instance, that gives us some labeled data, or you have historical data. And I'll go through an example here in a couple of slides. The other big advantage is that data, like machine learning models, are able to utilize many more features than a human ever could. And kind of the algorithms are non-linear, meaning that it really allows you to carve the data in a particular way that leads to better separation of kind of the malicious events versus the benign events. It is also less biased than heuristics because you're really learning from the data, and the algorithm kind of uncovers what these boundaries are. Now, bias can still be introduced through the labels that you use and, of course, the features that you encode, but generally speaking, it is less biased. The other disadvantage is that sometimes it is less explainable. So if you, for instance, have a machine learning model that says, hey, this transaction is malicious and there's a score associated with it, you may not necessarily know why the algorithm identified this particular transaction as malicious. There are some techniques that make machine learning models more explainable, like SHAP and LIME, that could be incorporated to kind of counter that. And then there's also drift that reduces the performance of the model over time. Now, it's an issue with machine learning models, but it's also an issue with heuristics as well, right? The attack landscape is changing, and your bot may become less effective over time.